Hi, in this video, we're going to take a look at evaluating our classification supervised learning models. Okay, so our idea here is I've built one or more models, and I want to check to see, do I have a good model? And really, when I say good, it's not yes, no answer, it's more of a gray scale. And we're going to have several different metrics and visualizations to help us understand what is the level of quality I've got in my model. Now we're going to be going over some major, uh, metrics that are in scikit-learn. There are more in scikit-learn that I'm not even going to touch. It has quite a bit of tools that we can work with. There are also other ways that we can approach model quality, such as AIC and BIC, that I'm not going to talk about. Those are really more of a statistics point of view. When we're talking about more predictive machine learning, we're going to use techniques that are more flexible for any type of model structure. All right, so when we're doing machine learning, so my goal is either probably prediction, maybe control, or possibly inference. Um, it's important for us to understand the quality of our model before we put it into production. And what we're going to do, we're going to take a particular metric that we choose to evaluate our model, and we're going to run that metric on our training data, our validation data, and our test data to evaluate how things are going. All right, so one big problem is that accuracy of the model for classification does not give us a complete picture. Why is that? Well, consider the situation where I have 99% are one level and 1% are the other. So if we're talking about mushrooms, which is the data set we'll talk about, let's say 99% of the mushrooms are poisonous, 1% are edible. All right, well, I can walk up, I go, you know what? They're all poisonous. Boom, problem solved. I've got my model, I've got my method, just say everything is poisonous. And you know what? I get 99% accuracy. But if you think about it, I have 0% accuracy when it's an edible mushroom. And why would I be building a model if I was just going to say a constant, everything's poisonous? All right, so we want to be able to pick up nuance. And these other metrics that we're going to talk about are going to pick up on this nuance aspect that accuracy doesn't, pick up completely. What we're going to end up doing in a real project is we'll actually consider several different metrics just so that we understand how well are we performing in terms of like true positives and true negatives and just accuracy overall. All right, we're going to be using the mushroom classification data set from Kaggle. Now, in the previous video, I went through and did my data preparation. And so we've got 1 is poisonous, 0 is edible. This is a switch from my R video on this. I went the other way around. For our data preparation, on this particular data set, every single predictor variable is categorical. And first thing I did was I imputed missing values with NA. NA is a good choice for missing values for categorical, because that is what someone will see when they're working with Excel. So when they see N/A in my work, they're more prone to accept it. Now, after that, after I imputed, I binned all the predictor variables into one of 3 levels, into 3 different levels: low, moderate, and high, corresponding to high has the highest fraction of poisonous mushrooms, moderate has in the middle, and low has the lowest fraction of poisonous by each individual levels. And so by doing this, the everything that's in low has a similar conditional target variable means on the 0, 1s. Moderate has similar conditional target variable means, and high has similar conditional target variable means. Now, I don't have a hard cutoff for what is low, medium, high. I'm just saying that I'm trying to put things into approximately equal sized groups. And so also, I tried to set it up so that we have approximately 1/3 in the low bin, 1/3 in moderate, 1/3 in high. That's not always possible, as we'll see as we take a look at the data, but it's an attempt. The more, so imagine I had like a states where I had 50 different states to work through. Usually the more levels I have, the easier it is to get approximately equal cuts in our bins. And then after that, the columns were converted over to dummy variables. Scikit-learn does not use categorical data anywhere at all. So what I have to do, I have to always have numeric predictor variables. All right, now when I load my data, one thing that I did was I created a dictionary of the data types. This can reduce computation time by quite a bit. If I don't do this, Pandas has to figure out what type of data is in each column. That's time that's taken, time burnt, figuring something out. If I've already gone through and loaded the data once, I shouldn't have it figure this out a second time. Also, if I have something like social security numbers, ID numbers, things that the computer will think is a number, it'll treat it as a number where I could do addition, which wouldn't make sense. It wouldn't make sense to add 5 to your social security number. That just is a meaningless operation. And so by specifying I want it to be a string or an object, I don't have any issues there. Also, I'm using PyArrow, which in my experience is the faster method to load data. All right, so here I'm using PyArrow. Here is my file path. And you can see here's my dictionary of data types. And you'll notice that everything is a string across the board. And so now I can get the results. So I've got this. All right, so now let's go ahead and prepare my predictor variables. And what I'm going to do is, so now I'm listing all my predictor variables I've got going on. I've got them set up here. I'm going to subset my data for the purpose of training. Here's my training set. I'm limiting it just to the predictors where it's the training partition. And I've got the Y target variable set up as the class. And now I want to do a logistic regression model. Well, if I do this, something that's going to happen is that I've got a lot of predictor variables in there. I need to do feature selection. If I don't do feature selection, I'm just throwing everything into the pot of my model. And it's just kind of like going into a kitchen and throwing every ingredient you have possible into your pot. You're not going to make a very good stew. It may be edible, but you could have done better by being judicious about what's in and out of your recipe. And so what I'm going to do, I'm going to use Lasso to do feature selection for me. The reason why I'm using Lasso is because I don't have a predefined number of predictor variables to include. The other methods in scikit-learn that I've taken a look at say, hey, so you have to specify how many predictor variables do you have. Well, I don't want that method. I want to say, hey, if it's helpful, include it. If it's not helpful, exclude it. And if it improves the model, keep it. If it doesn't improve the model, get rid of it. All right, so now something to be mindful of is that when I do this, I can break up my levels if I have. So starting out with my data, I've got low, moderate, and high for my categorical predictor variables. And it's likely that 1 or 2 of these will get kicked out. Possibly my stakeholders would want all levels included in the model. For this situation, I'm not going to worry about that. What I've done at work in those situations is that if one version of a categorical predictor variable has been retained, one of its dummy variables, then I include all of them in the modeling process because I have to make sure my stakeholders have faith in the model. That's more important than preventing overfitting. And the reason why I'm doing feature selection is that the more predictor variables I have, the more prone to overfitting I am. So I want a smaller, best subset possible. All right, now I'm going to go ahead and fit the lasso model. You'll notice I'm using the L1 penalty. Now for the solver, I have to use the liblinear solver. The default one won't run with L1. And so now I've got my predictor. So here's the list of predictors after I've done feature selection. And this is how I pulled that originally. And I just copied and pasted. That way, in case, off of random number generation, I don't have a different set of predictors going down the road. All right, so now I'm going to fit a vanilla logistic regression model. I always feel like whenever you're doing classification, you should always do a vanilla logistic regression model because we theoretically understand that one the most of all classifiers. we should also do a decision tree. If I'm doing a regression target, I'm also going to do a linear regression one, multiple linear regression, vanilla regression, and I'm going to do a decision tree also. These are very simple models, well understood. This is always a good place to start in your modeling process, and that's what I'm doing here. All right, and so here I've got my logistic regression model, and we use maximum likelihood estimation to estimate the coefficients. That's in contrast to this version of logistic regression, where we use lasso L1 penalty to shrink our coefficients. Uh, if I have more predictor variables than I really should, if I have some junk in there, I probably should have kicked out. Using the L1 or L2 penalty will help mitigate that to some degree. It's more important that I do judicious feature selection on our own than relying on the algorithm to do feature selection for us, though. All right, and so now let's go ahead and get our values from the model. So I'm going to have a classification of the predicted value. I'm going to have the modeled probabilities, and also I can use the log of the modeled probabilities also. Now, the log of the modeled probabilities is best used when we have smaller probabilities. It's never come up for me at work, but if I had to interact with very small probabilities, this would definitely be the way I would go. Now, one thing to notice about the model probabilities is that they're going to get spit out in two-dimensional arrays. If I had 3 levels and it was a multinomial project, I would have 3-dimensional array. And if I had 10 levels, a 10-dimensional array. So we need to adjust to this. And you'll notice that on this step right here, I am just saying, hey, I just want the probabilities that correspond to 1 of being poisonous. 0 would correspond to being edible, the model probability of being edible. Now, here I've got the actual target, the true value, the predicted class, and then I have the modeled probability of being poisonous. And you can see that just at first glance, my model is doing very well. That's because the odor predictor variable is very, very powerful for this particular project. All right, now here is just a look at the count of my validation, training, and test partition. All right, so first one I'm going to show you is a classification report. I put this first because this is a fast way to get basically a bunch of metrics vomited out to you. And so what this is going to do is that this is going to go level by level and give me precision recall F1 and support. Support is the count. So here is the true value. Here is the precision recall F1 and support. Now all my statistics look really, really good because that odor predictor variable is really, really powerful. It's not because I made the greatest model possible. It's because basically this data set has handed me 4 aces and I'm not screwing it up. All right, now here, this one is for my training data. This one is for my validation data. And this one is for my test data. And so we can just kind of see, what's going on for each of these. And this one's nice because I get it so quickly, so fast, and it breaks down the actual results individually. Now the confusion matrix is going to set it up so that I can see how often did my model get it right by true positive, true negative, but also how often did it get it wrong by false positive, false negative. So a true positive is when the model said positive and it was right. True negative is when the model said negative and it was right. But when it's a false positive, the model called positive, but it was negative. If it's false negative, the model called negative, but it was positive. And we can set this up. And the rows correspond to the truth, the actual target variable value, and the columns correspond to the modeled values. And so we can work this out to get these. Now I'm going to go through a bunch of statistics that we can use the confusion matrix to compute in a moment. Here is my confusion matrix for training. Here's my confusion matrix for validation. You notice I've got 2 errors and I've got 4 errors on my test set right here. All right, so it said that the model said that 4 times in the test set it was poisonous when in fact it was edible. It said that twice the mushroom was poisonous when it was edible. Now accuracy is the simplest one possible for a metric. This is how often did it get it right proportionally. Now, remember, accuracy is not a good metric if I have imbalanced data. If my data is like 50-50 for the positive negative values, then accuracy is excellent to use. But the more lopsided my data is, the more, if let's say I had 99% positive or 99% negative, accuracy doesn't perform so well, because if I just say everything is positive or everything is negative, I nail a 99% accuracy without doing anything. There's no point in modeling if I'm going to do that. So here, accuracy is not the best if I have imbalanced data. And so here I can see my accuracy scores on my training, validation, and test. When I see a gap between train and validation, or train and test, that's an indication I have overfitting. And so here, there really isn't a meaningful gap. So I feel like overfitting is not a problem here. Now, balanced accuracy, what this does, this considers the accuracy when it's only positive for the truth and only negative for the truth, and then takes the average of them. And so this is a better approach when I have imbalanced data. Next one is precision, recall, F measure, and support of each. And so this is going to just spit out what we looked at previously a moment ago in a different format. Now, I put this here because in a moment, I'm going to go over each of these. So let's talk about sensitivity. Sensitivity is true positive divided by true positive by false negative. So the denominator, all the times that's positive, when it was positive, how often did we get it right is sensitivity or recall. You notice that we're nailing it on this one. Specificity is when we have, in the denominator, we have true, negative, false, positive. So this is all the times that it was negative. How often did we get it right, given that the truth is negative, is specificity. Now, precision is all the times that we called positive. How often did we get it right? Now, the F1 score is a balance between precision and sensitivity. It's beneficial when the class distribution is uneven, and you want to measure that considers both false positives and false negatives. The F1 score can be interpreted as a harmonic mean of precision and recall, where an F1 score reaches its best value at 1 and its worst at 0. The relative condition of precision and recall to the F1 score are equal to each other. We also look at the binary classification, positive and negative likelihood ratios. And here, this is typically used in medicine to identify the positive negative class to the presence and absence of a disease. And so, this is, just really looking at, that ratio of the positive and negative in this one. We also get our average precision score. And so here, this is taking the precision over a range of possible thresholds for saying this is poisonous or edible. So, if I'm really, really hungry, I could say, hey, it's edible if the probability is less than 3/4, 0.75 instead of 0.5. By increasing that threshold, I'm going to have, my model is going to say fewer cases are poisonous and more are edible. Well, that leads to the potential of more false negatives on this one, and missing cases that were poisonous. This is a balancing act. Our classification models, very much, when we talk about our thresholds, very much are a balancing act between false positives and false negatives. Here, average precision is I'm going over a full range of thresholds, and then I'm checking my precision. We can also look at the precision recall pairs. Remember that they look at things in different ways. And so here's the output that's just kind of like vomited onto here. I could work with this later if I wanted to. Now, the Breyer score, what this one does, this takes the mean squared error between the probability and the classification. And so if the true value is 0, this is going to be the model probability squared. If the true value is 1, this is 1 minus the model probability squared. And then we take the average. So here, this is really just mean squared error with the guy's name on there. And so here we can see that our model did pretty well. Our model is doing pretty good. All right, next one is going to be related to the receiver operator characteristic curve. All right, so the receiver operator characteristic curve, ROC curve, is going to be considering, well, what if I take a very small threshold for declaring poisonous, or a little bit bigger, a little bit bigger, a little bit bigger, all the way up to very high threshold of like 0.99 to consider poisonous, what am I going to end up getting for my sensitivity and my specificity? Consider these simultaneously. And I'll end up actually having a curve. Well, this curve is going to have an area between the x-axis and that curve. That area is called the area under the curve. And that area is a good evaluation of how much control do I have if I start tinkering with the thresholds, if I start throwing those levers. And increasing the threshold will usually increase the number of false negatives. Decreasing the threshold will usually increase the number of false positives. So there's advantages and disadvantages to changing my cutoffs. The AUC and the ROC curve tell me like how much control do I have and how much will I lose if I start tinkering around with it. And this is across a whole range of thresholds. For AUC, 1 is perfect, 0 is perfectly bad. And if I was to do random guessing with a uniform random number generation based off of the threshold I set up, then 1/2 would be my AUC. And so using that, we have a baseline of if it's below 1/2, I'm worse than random guessing with my model. And so here we can get our AUC. Scikit-learn has 2 ways to compute this. Here I'm using scikit-learn's, like doing it directly. The other version uses the ROC curve output function. Now here, let's visualize it. And so here, the orange is from my model. The blue is random guessing. So this is a very, very good model. You can see that this is all the way up. It looks like a square. This is the ideal. Typically, we'll see something that's more curved. It'll look kind of like a bow with that dashed blue line. And we want this curve to be as big as possible. And each point along the orange curve corresponds to a different threshold for saying poisonous or edible. If the model probability is like here, let's say it's 0.1 is the threshold, we're saying it's poisonous. So probability 0.1 or greater, poisonous. Probability 0.2 or greater, poisonous. Probability 0.4 or greater, poisonous. 0.5, 0.6, 0.7, 0.8, 0.9, and then a 1. And so we see that we have a really good model off of this. Now, another one that I use, I like to put box plots of my model probabilities just to see what I'm getting for range. This is a very solid model, so I don't get to see much of a box plot. But typically what we'd have a box plot of the modeled probabilities, and where the true value is 1, and here is every time that the true value is poisonous, here is the model probability. Every time the true value is 0, here is the model probability. And what I want to see the box plots very, very different. I want to see the 1s have the probabilities very, very high, and the 0s have the probabilities very, very low, like I have here. If I see like there's no indication of 0, 1, like they're like, both box plots are going all the way up, all the way down, that means I have a junk model. All right, homework. Build a logistic regression model. Any penalty you want, don't care. Actually, you can build any model you want. But I'm saying logistic regression in case you're new to machine learning. If you have experience with machine learning, do your favorite model structure. I don't really care. I just want you to execute these metrics, and I want you to visualize that box plot and ROC curve. That's all I've got for you. Life is short. Do math.